This video is about quadratic function models. So when we look at a quadratic function, the standard form for a quadratic function is f of x equals ax squared plus bx plus c. F of x is another way basically to say y. Ax squared is considered the quadratic piece. Bx is considered the linear piece, and c is considered the constant. So sometimes we don't know if something is a quadratic function or not unless we simplify it. For example, these two are very similar, but when we simplify through distribution, the first one gives us 3x minus 15, the second one gives us 3x squared minus 15x. Only the 3x squared minus 15x is considered to be a quadratic because of the squared piece. It has a quadratic piece. So sometimes you have to simplify the stuff before you can decide if it's a quadratic or not. Once you know it's a quadratic, the graph of a quadratic in its most basic form looks something like this. Now there's a line down the middle, and on either side of this line there are points that correspond to each other. If one point is called Q, the other one would be called Q prime. They correspond to each other because they're reflections across that line. It's like here, if this was P, and let's say we were 2 spaces away from the line, then we'd have to go 2 spaces away in the other direction to find P prime. So we do have a whole bunch of corresponding points, and we don't have to be centered on the middle of our graph. My parabola could be up and to the right like it is, and if I had a point here, A, so it's 1 space away from the vertex point, the bottommost point of the graph. We'd have to go 1 space away in the other direction to find its corresponding point of A prime. So something else you can do with quadratic function models is you can take 3 points and find the quadratic that would fit these 3 points the best. So to do that, you're going to take the standard form y equals ax squared plus bx plus c, and you're going to find 3 equations, plugging in the x and the y value for each equation. So first I'd plug in 3 for y and 2 for x. Simplifying, I would get 3 equals 4a plus 2b plus c. So next we'd plug in 3, 13. Y is 13. We plug in 3 squared and 3 here. 3 times 3 is 9, so we'd have 9a plus 3b plus c. And then 4, 29, we plug in 29, and 4 squared would be 16a plus 4b plus c. So the question is, how do we solve something like this, where we have 3 equations that we're working with? So we're going to have to solve this using a method called substitution, or you could use elimination as well. Let's actually go with elimination. It's a little bit easier. So I'm going to take the first 2 equations, and I'm going to multiply one of the equations by a number that would allow me to cancel some things out. So since our c's only have a 1 in front of them, I'm going to multiply this top equation by a negative 1, which would give me negative 3 equals negative 4a minus 2b minus c. The second equation I'm going to leave the same. I'm going to add these 2 equations together now. Negative 3 plus 13 is 10. Negative 4 plus 9a is 5a. Negative 2 plus 3b is 1b. So b. Negative c plus c cancel each other out. So now we're going to do the same thing with the last two equations. I'm going to multiply the first equation by negative 1, and then combine the two equations together. So we would have negative 13 equals negative 9a minus 3b minus c. Our second equation is 29 equals 16a plus 4b plus c. Again, we add. Negative 13 plus 29 is 16. Negative 9 plus 6 is 7a. And negative 3 plus 4b is 1b. So now we have our two equations that only have a and b. So we don't have parentheses on either of these or anything, so we can, again, do our elimination method. We don't have to do any sort of simplification. We can do elimination method. This time I'm going to get the b's to cancel. So I'm going to multiply the top equation by negative 1. So negative 10 plus 16 is 6. Negative 5 plus 7a is 2a. Negative b plus b cancels each other out. To get a alone, I'm going to divide both sides by 2. So we get a equals 3. So now we're going to have to go back and plug that in to find b. If I plug in 3 for a, 3 times 5 is 15, and I'd have to minus 15 from both sides. So negative 5 equals b. Then we go back to one of our original equations and plug in what we get for a and for b. To find c. So we get 3 equals 4 times 3 plus 2 times negative 5 plus c. 4 times 3 is 12. 2 times negative 5 is negative 10. 12 minus 10 is 2. Minus 2 from both sides. So 1 is equal to c. So it is a longer process. There are a lot more steps when you're solving a system of equations that big. So the last topic for this section is deciding if a certain point fits a certain quadratic. So do the points fit the quadratic? So we're given a certain number of points. Negative 1 comma 6, 1 comma 4, 2 comma 9. And they'll also give us a quadratic to check. Say we're using y equals 2x squared minus x plus 3. So all you're going to do is plug in the x value they give you and see if it comes out with the y value that it says it should. So our prediction is if I plug in negative 1, it should come out positive 6. So simplifying, negative 1 squared is positive 1. A minus minus also makes this positive 1. 2 times 2 is 1. 2 times 1 is 2, 2 times 1 is 2. And adding that all together, 2 plus 1 plus 3 is 6. That point checks out. Now we try plugging in 1. Y equals 2 times 1 squared minus 1 plus 3. We simplify and hope we get 4. If we don't get 4, then no, these points do not fit the quadratic. One squared is 1, so 2 times 1 up front again. 2 times 1 is 2. 2 minus 1 plus 3 is 4. So that point checks out. Then we do it again with 2. 2 times 2 is 4. 2 times 4 is 8. 8 minus 2 plus 3 gives us 9. So all 3 points check out, and those points are part of a quadratic graph. So that ends our discussion on quadratic function models.